Unit, Aryan, that we just finished, we basically asked if we have a moving current through a magnetic field, it will feel a force. We're going to reverse that question. If we have a magnetic field and we apply a force to a wire, will we get a current? We're going to see if we can figure out how to generate electricity. And so we started out looking at what we called voltage induced by motion. First thing I said to you is we're going to start to use an archaic term for voltage called EMF. It stands for electromotive force. It's not a force, it's a voltage. It's this funky E. You're going to notice today why we're doing it, because today we're going to have equations with V's and EMFs in them. And the smaller V is a speed, the bigger EMF is voltage, and that way we're not getting the V's confused. In fact, today you're going to get an equation with an EMF, a big V voltage, and a lowercase v. This is one of the reasons we do that. We started looking at the idea, well, first of all, we generated an equation for the EMF, for the induced voltage between two sides of a rod moving through a magnetic field. It was BLV. Everything had to be at right angles. We played around with it a little bit. We looked at what if they weren't at right angles. You didn't get much separation of charge. Then we started to say, what if we had the bar sitting on conducting rails? Well, we said now if you moved it, you would actually be creating a current. You would be inducing a current, and you would be creating the equivalent of a battery. And we left off by saying, look, as soon as the current starts to flow, not only do you have charges moving to the right because you're pulling on the bar, as soon as the current starts to flow, you also have charges moving that way. We pointed our thumbs down the page, magnetic field out of the page, and we said, you know what? There's going to be a force to the left. And you would feel this. If you were trying to slide this bar across the conducting rails, as soon as you started to tug on it, Taya, you would feel this strange force resisting you. I got out, I have a couple of rechargeable flashlights. These are the ones that you turn by a hand crank. If you turn these, they don't turn easy. It's not because there's no friction. You're actually feeling that force, that one there, opposing you. Now, we haven't talked yet about how that force just manifests itself when something is spinning. That's going to be tomorrow's lesson. We're going to look at what if you turn this into a coil of wires and spin it instead of a single bar moving. But we start with this concept because it's a lot easier to wrap our brains around. Played around with some numbers, and I think we got to example 10. Oh, it says pause here, show electromagnet. Let me pause. So I showed you the electromagnet. Now we're going to ask, so up until now, we've been pulling this, and we've been getting a current out the other end. What if we supply a current? Can we get motion? And yeah, here's the physics of a railgun. Okay, so in this circuit, the wire strip is initially at rest, but there's a power supply in the circuit. Fahim, see the battery? From the battery, is the current flowing down the page or up the page? So let's draw a little I right there, and let's continue to follow it. I think through the wire, it's traveling up the page in that little section, yes? So part A says, what's the direction of the current? Well, you know what? The direction of the current is counterclockwise. I'm going to abbreviate that from now on as CCW. What would be a good abbrev for clockwise? CW, okay, I'll use those two. Sometimes you may see ACW for anti-clockwise, especially if I've stolen something from a British website. They call it anti-clockwise, not counterclockwise, but CCW or ACW is in the opposite direction of a clock. If you're not sure what direction that is, look up. There's clocks in my room, okay? B asks, what's the direction of the magnetic force on the strip? Okay, let's see. The current is moving up the wire. What direction is the magnetic field, Eliana? It tells me. It tells me. Out of the page. So everybody point your right thumb up the wire. Magnetic field fingers out of the page. Yeah, Fahim, which way will this feel a force? This is going to feel a force in this direction. F is to the right. So what's going to happen? Well, that strip has an unbalanced force to the right. What must it do? It's going to accelerate to the right. It'll start to speed up. We call this a rail gun. This has a few neat applications. Oh, I have a video. Yes, I do. I'm not going to show you the second one, but the first one is okay, Mr. Dueck. What was it called? This is, I think I took this from a U.S. military site. So there's the projectile. Now a disadvantage with this is it's big and unwieldy, but one advantage with this is you're not getting the projectile to go fast because of an explosive. You don't need any explosives. So you're not worried about your ammunitions dump blowing up on you or anything like that. If there's a fire, if the weather's getting hot, if someone drops the projectile, you're not worried about any of that. All good. This is a projectile. I don't know quite how they sent a current through this or if they had a rail behind it just pushing it. I don't know. But this is a rail gun. It's going probably, I think it was 7 or 8 times the speed of sound. It's going crazy fast. It's just punching its way through plate steel pretty easily. It's got enough kinetic energy that it's going to keep going. Okay. If you look really close, as part of it, they spin it. That's what gives it stability, like when you spiral a football. Oh, like the kendama toy when you spun the ball that kept it central on an axis. If you spin a projectile, that'll keep it central on its axis, makes it more stable. And then it looks like what this does at the very end is it breaks up into smaller fragments, which is really kind of terrible. It's a weapon of war. They're not meant to be nice and friendly. That's why war sucks. But the physics is at least okay. Example 11. Example 11. Says this, as the strip speeds up, what happens to the induced voltage? Well, what's my equation for induced voltage, Aiden? Now, your hint is it's the first equation in this new unit. Yeah, induced voltage we're using the EMF symbol for. It's BLV. Well, as it speeds up, what's going to happen to the induced voltage? Be obvious. As V gets bigger, what happens to E? Okay, now let's talk about how the induced voltage is going to work. So first of all, which way is this strip moving? Which way is the strip accelerating? Sorry, to the right. So I'm going to, do me a favor, draw our little token proton right there. Now it's moving up the page because of the current, but as soon as the strip starts to move, it's also moving in which direction? To the, looking for where it starts with letter R. Everybody, everybody point your thumbs to the right. As soon as it starts to move, magnetic field out of the page, what direction will that proton feel a force? Down against the current. So now we're going to have an induced current going in this direction. In fact, what you can draw here is there's going to be the equivalent of a battery pointing that way. We're going to have two opposing batteries, two batteries facing each other. So what's that going to do to the current? Well, first of all, because I total is V total over R total, V total is going to decrease. because this would be like going up the chairlift and then down the chairlift a little bit. You're not getting the same voltage as when it was at rest. And so if V total is getting smaller, Ashley, what's going to happen to I total? Yes, I total is going to decrease. So what's going to happen to the magnetic force? Ooh, Ella, what's the equation for magnetic force on a wire? You got this. Is that the force on a wire, or is Q an individual charge? Which one was the force on a wire? This is Bill, right? Well, if Ella, if current is getting smaller, what happens to the force on the wire? Okay, the force is decreasing. The force is decreasing. And Petra, F equals what? Is the mass of the bar decreasing? Be obvious. No. So what's getting smaller then? Yeah, so acceleration decreases. It's still speeding up, but not as fast. And a few moments later, it'll still be speeding up, but not as fast as it was before. This is one of the few times we're dealing with a changing acceleration. The acceleration is going to get smaller and smaller until eventually the acceleration is going to hit exactly. That's the maximum speed of your railgun. All right. It says explain your answer using relevant principles of physics. Hopefully we walked through it orally. You're okay with that? This has some neat applications. This is seen as a means of launching vehicles from the International Space Station. If you're launching spaceships from a space station, you probably don't want to turn your rockets on really close to the space station. That can't be good. And so the theory would be you would have a couple of really big solenoids. Hello. Oh, what happened? That was weird. Undo. There we go. A couple of big solenoids, and those solenoids would get their current from solar cells. Lots of solar power on the International Space Station. And you would also have a current. You would run the current through the spaceship itself. You would run the... Okay, everything's going a little haywire here. Pause for a second. What you would do, Marcus, is you would run a current through the actual spaceship. You'd have a conducting bar along the bottom or something like that. So here is our token proton right there. What direction is the proton traveling, Anna? Down the page. What direction is the magnetic field? Which direction will the spaceship feel a force? Use your right-hand rule and figure it out. Yeah, it's going to feel a force that way. This would be a way to launch it away from the space station with no moving parts. Once it left the rails, well, now Newton's first would kick in outer space. It would just keep going in a straight line at a steady speed. And once it was a safe distance away, now you could turn your rockets on. I don't believe they've built that, but that's certainly one of the ways we could do an easy space launch. Easy peasy. Another application or another place this shows up is in electric motors. So you'll notice here, as we moved faster and faster and faster, we were generating a back voltage, an opposing voltage. It's called a back EMF or a back voltage. And in fact, eventually, well, what's the smallest the current can get as a number exactly? 0. You get no current flowing through the system. Something very, very similar with electric motors. With electric motors, when you rev them at their maximum, you actually generate a back voltage that's identical to the source voltage. The maximum speed an electric motor can spin is when that occurs. We haven't looked at we looked at electric motors a little bit, but we'll do a whole lesson on back EMF, on back voltage. Example 12. As this strip continues to speed up, the induced voltage will continue to grow. What happens when the induced voltage is equal to the supply voltage? So here we have our current going this way, but as soon as it starts to move, we have the equivalent of a battery going that way, an induced voltage. What happens when the induced voltage, it's a terrible V, equals the supply voltage. Well, what will the net voltage be if we have two identical voltages in opposite directions? If you go up 120 volt chairlift and you go down 120 volt chairlift, what's your net voltage? Well, if I total is V total or V net over R, what will your total current be if V is 0? And so if FB equals Bill, Petra, what will the net force be if I equals 0? What's the correct answer? A, B, C, or D? Got to be A. Net force is 0. And that constant speed would be your maximum speed from your railgun. Hey, you know what? Let's get an expression for that. Turn the page. So here's our railgun. Right at the beginning, the EMF is 0. We haven't turned anything on yet. And so right at the beginning, V, let's call this V here, V source. I'm going to use an S as my abbrev. But as soon as the current is moving this way, as soon as it starts to move this way, now there's going to be a current flowing that way. We're going to get the equivalent of a battery like that. And in fact, the maximum speed is going to be when V source equals the induced EMF. Aiden, how do I calculate the induced EMF? What was the equation? And source, what? Oh, V equals what times what? Get the V by itself. This is the maximum speed of your railgun. I don't know if I'm going to ask you that on a test, but just kind of for giggles, railguns are kind of cool. Let's do one with some numbers. Oh, I showed you the science behind railgun electro boom style already, right? Where he does the Lion King song for the right hand rule. Okay. Example 14 says, for each instance below, find that. This is the same picture before and after. This is right when we turn the switch on. So what I'm going to say is, let's just draw a line down the middle of the page. Okay. And this is after we've turned it on, once it gets going, well, to 8 meters per second. Okay. Ruby, what does A want me to find? The induced voltage is BLV. The induced voltage is BLV. Oh, the first one is easy because what's V? In your head, what's the induced voltage right when we turn the switch on? 0. But once it starts to move, it's going to be magnetic field 0.35. L, oh, strip length it says is 4.1. I have to look for that. And V8. What will the induced voltage be, Ruby? I'll call it 11.5. Is that okay? Volts. And if you're looking for kind of a direction, it would be in that direction. Nicole, what's B want me to find? Well, I think right now it's 320 volts at the beginning. I just lifted that right from the battery. Ooh, what will the net voltage be now? Not going to be 320. How will I calculate it? Nope. Nope, not yet. We're gonna use IR to find I, which I think is part C, I bet you. Right now, what's my source voltage from the battery? What's the opposing voltage? How big? How can I calculate the net voltage? Yes. 308.5. Double check me. I might have carried a one wrong. Is it 308.5? Yeah. And by the way, because this is speeding up, a few minutes later, it'll be 305, then 300, then 270, then 250, then 200, then 100, then 50, then eventually zero. That's when you hit maximum speed. Kyle, what's C want me to find? Now we'll use Ohm's law. Current is going to be V over R. Initially, it's going to be 320 take away, divided by 8.5, which is what? And I think it also asked for a direction. I guess the current would be go this way, this way, this way, clockwise or counterclockwise. So I'm going to put a CW for direction. Current is also going to be V over R, but it's going to be your net voltage because that's your total voltage now. It's going to be 308.5 divided by 8.5. It's going to be smaller. Not by much yet, but a little bit smaller. Yep. Yep. By the way, do you know what generates heat in electric devices? Current. More current, you lose more energy to heat. They're less efficient. Pause the video for a second. Uh, the more current running through your electric device, the more energy you lose to heat. As this goes faster and faster, what happens to the current? Bigger, smaller, or stay the same? Smaller. What happens to the amount of heat? Smaller. Electric motors, one of the reasons they're so much more efficient, they're at their most efficient when you're revving them at their maximum. Is a gasoline engine at its most efficient when you're revving it at its, that's when it's at its least efficient. Electric motors, rev them full, that's when you're losing the least amount of energy to heat. Okay. What was that? Oh yeah. They overheat when they're under load running slow. And yet to cool them off, rev them up. D. Oh, well, Eliana, what's direction? Sorry, Kyle, for part two. I think it's still clockwise. Yes. Eliana, what's D want me to find? Magnetic force. Okay, magnetic force on a wire from your formula sheet. So F equals something. So we're looking in the magnetic section. Not QVB because that's on a charge. Oh, you did this one. Magnetic force on a wire. Didn't you give me this one early? Oh, no, you one. Bill, right? Yeah. Bill. Do I know the magnetic field, Eliana? It was 0.35, I think. Yes, I've scrolled down. Was it 0.35? Teslas, I think. I 37.6. L 4.1. That for me, kiddo? What do you get? $54? Then it wants the direction. Well, let's see. Charges are moving down the page, magnetic field, oh, to the right. What about the right-hand side? You know what? It's still going to be Bill. In fact, I think you could just backspace and all you're going to do is change the current number. Yes? Current is now 36.3, not 37.6, 4.1. Backspace and edit. Force should be a little bit smaller, so it won't be accelerating quite as much. Still speeding up though. What do you get? 52.1, I think. Is that right? Newtons also to the right. A few minutes later, the force will be smaller, but still speeding up. But eventually, you'll reach the point where when V source equals the EMF, your net voltage is zero, your net current is zero, your net force is zero. That's your maximum speed. So that's the physics of a rail gun. What's your homework? Number 1, 2 is good, 3 is good, 4 is good. Ooh, power. Oh, power would be V times I, or I squared R, or V squared over R. I can handle that. If you want to, you can try 5. It's nice and algebraic. You can skip 6, although it's kind of cool. You can skip 7. 8 is nice because I want to have spaceships. You can skip 9. That's really not much homework. I know you folks are having like grad stuff and things coming up and other events. So if you want to get a head start on the ultimate review, you can also tackle from the ultimate review 1, 6, 8, 16, 35, 40, and 43. They're all doable if you want to get a head start. I'm going to hit stop.